Hey there, Stat Nation. This is chapter 9, day 8. We're going to be doing some homework together today. So get a piece of paper out, get your calculator out, and I'll talk through this and give you some extra information. So pretty good stuff here. We're starting to do inference for proportions. So not means, we're dealing with percentages now to see if a test statistic from a percentage will give us evidence to prove something or not. Okay. So it starts on, I'm going to be doing chapter 9, assignment 4 and part of 5. So if that helps. So go to page 570, number 31. And the first question says, it says, check the conditions to see if we've met the conditions. So Jason reads a report that says that 80% of high school students have a computer at home. He believes that the proportion is smaller than 0.8 or 80% at his large rural high school. Jason chooses an SRS of 60 and records whether they have a computer at home. All right, so the conditions, remember the acronym SPIN. And I'm going to write what I usually do. I'm going to write assume the following, or assume ... That's all you need to do, assume a couple things. One is the S. Is this a representative sample? I have no idea how he collected his data. So I'm going to assume we have a representative sample, representative sample. Great. Okay. Now, the P is the 10% rule, or population 10 times bigger. Remember, the reason you don't want to sample more than 10% of the population is you don't want to destabilize the standard deviation. When you oversample, the law of replacement starts changing percentages every time you do it significantly and destabilizes it. And we need a stable standard deviation to do some inference, okay? So assume there are greater than 600 kids in his school. Now, we don't know if that's the case because it just says large rural high school. I'll put that parentheses, large rural high school. So I'm assuming that means there's more than 600. Okay. All kids are independent. What you're really saying in all kids independent, and you might say this, is that you're assuming that you're not getting people that live together, same households, because then you'd have a double count or whatever. So that's really what you're saying in this case. And then the last N is, do we have enough samples to calculate a normal curve? Remember, when you're dealing with a mean, you got all kinds of ways to establish normality. If you have more than 30 samples, you're going to say the central limit theorem guarantees normality because I have more than 30. If you have less than 30 and you have the data, you're going to make a box plot and say, see, the data looks relatively normal. If you don't have either one of those, you're going to say, well, I'll just assume it's normal. Okay. So anyhow, there's only one way in a proportion. You're going to go N, 60. I'm going to multiply it by P, 0.8. Is that bigger than 10? It is. It's 48. 48 is bigger than 10. And then the next one is 60 times 0.2. Is that bigger than 10? Absolutely. That's 12. So we have enough samples for normal. So I'm going to put enough samples for normal. And you should write a little bit on these prompts, kind of walk the reader through the logic process. Don't just dump out kind of what I've taught you. Put it in context of the problem. Write a little extra, like large rural high school, a little hint there, enough samples for normal, things like that that really show that you know what you're doing, okay? So there's that. All right, so the next one is on page 570, number 33. Why aren't the conditions met for a z-test for proportions? Why not? Well, you toss a coin 10 times and perform a test if it's fair or not. 0.5 versus not 0.5. Okay, this is not this right here, right? Okay, well, I mean, if you think about it, 10 coin flips is not going to prove if a coin is fair or not. If you flipped a coin 100 times and you got 90 heads, that'd be like, whoa, that's weird. But if you flipped a coin 10 times and got 9 heads, that's not super strange. Okay. So you can tell just by looking at this that the requirement that you're violating is the last one in the acronym SPIN. We don't have enough samples N for normal. So I'm going to say they are not, because N 10 times P is not greater than 10, and N times 1 minus P is not greater than 10. Okay, they're both 5, which is, so they don't have it, not nearly enough. You actually need 20 for this particular study. Okay, that's easy. All right, next prompt, page 570, number 35. Jason reads a report that says 80% of high school students have a computer at home. He believes that the proportion is smaller than 0.8 at his large rural high school. Jason chooses an SRS of 60 and records it. In his survey, 41 had a computer at home. All right, so calculate the test statistic. The test statistic is going to be, in case you want to know what that is, that's either going to be a t-score. It's either going to be a t-score or a z-score, okay? So a t-score for a mean, or a z-score. We're obviously doing a z-score, okay? So what is the test statistic? We're gonna check it out. We're gonna figure out a t or a z, by the way, is how many standard deviations you are above or below the mean. Remember, if you're over 3 standard deviations above the mean or below the mean, that's considered unusual. Okay, so we're looking for that. And if something's unusual, that's going to give us some proof, give us some evidence, I should say. All right, so pretty simple. We are going to, our z-score is going to be, in this case, if you remember how to do a z-score, is going to be 0.8, okay, minus, and we're going to do whatever 41 out of 60 is real quick. So let me bring my calculator in here. Okay, so I'm going to do 41 divided by 60. Okay, is 0.68. I guess 0.68. Probably that's good enough. 0.68. Okay, so we're going to go for the test statistic is going to be 0.8 minus 0.68. This is rounded. It's about 41 over 60 is about 0.68 divided by, and it's going to be, the standard deviation is going to be 0.8 times 0.2 divided by 60. Okay, so in its raw form, that test statistic is going to be p hat minus p. I actually have this backwards. Okay, this is actually backwards. 0.68 minus 0.8. There we go. 0.68 minus 0.8 divided by this particular standard deviation, 0.8, 0.2 over 60. In its raw form, it's p hat minus pi, or p, right, divided by pi 1 minus pi over n. Okay, that's the raw form of that. It's on your formula sheet. And by the way, what I call pi, most publications are calling p. Okay, just without the hat on it. That's the population notation. Okay, so let me do this again. Let me clear this and do this again. Okay, because I'm a little sloppy there. So 0.68, which is 41 out of 60, minus 0.8 divided by this, okay, which is 0.8, 0.2 over 60. Okay, standard deviation. Right. So that's the test statistic. I think it comes out about 2.2 something or other, 2.25, 2.3, somewhere in there, depending on where you round it, approximately, something like that. Okay, because what's going to happen is we're going to use technologies, how we're going to do this to find the p-value. This is how we're going to do this. So let's go ahead and jump into the technology piece. You're very unlikely to do this thing by hand anyways. Very unlikely. Okay. Let's go to technology to do this. All right. So let me bring the calculator in here. And we're going to go stat tests. And we're going to go one prop Z test number 5. Okay. Got it set up. So there's your P 0.8, 41 over 60. And it's going to be less than. Okay. It's going to be less than on this. Because Jason thinks it's actually less than 80%. And his test statistic is 68%. So it is slightly less. Okay. And so I'm going to go to draw on this. And we're going to get the answer. So yeah, there's our test statistic, negative 2.26. I knew it was a little bit below everything, negative 2.26. And the p-value is 0.0119. Okay. So our test statistic was negative 2.26. All right. And there's the p-value, 0.019. So it's just above the 1% level. So at the 5% level, he's got some evidence to suggest that his school actually owns less than 80% of the households have a computer. At the 1% level, he hasn't proven that or shown that. But there's your test stat, negative 2.26, and there's your p-value. You're probably going to do that on technology. Okay. All right. So, and there's the area and normal curve. So I've shown that on this thing. That's pretty cool. Okay. So let's jump into page 570, number 37 now. Okay. So we got this 0.5 versus greater than 0.5 kind of deal here going. And again, what I usually call this pi. A lot of the book calls it p, no problem, either way. And there's your test statistic, 2.19. Now, what's interesting is if they give you the test statistic, they've done a lot of the work for you. And then it says, what conclusion would you draw at the 5% level? So remember, if you recall from the normal curve that we learned a long time ago, we start with raw score, Z-score or T-score, and then the percentile rank. We're already in that middle level. We're already there. We don't even have a raw score in this problem. We don't have it. It's just some generic problem. So the Z-score is 2.19. Now, what happens when you do that is you've taken out the stat tests part of the calculator. You can't use that. So you're going to have to do something else. But you should know how to do this from your past. Okay, so let's look at this. Okay, so the Z-score is 2.19 and it's greater than. So what we're going to do, okay, is we're going to go back to our calculator and back to what we learned a long time ago is we're going to go second distribution and we're going to go to normal CDF. Okay. All we're going to type in is 2.19. It's greater than. So the area above that, the upper level is put in some infinity number. And that is going to be the p-value. Do you remember that? How to do that? So that comes out 0.0143. Go to 4 spots. 0.0143. Remember that? 0.0143. So this is 0.0143. What conclusion we draw at the 5% level? At 5%, our conclusion would be reject HO. Because that number 0.0143 is less than 5%. And then I'll start my sentence frame. We have significant evidence to suggest ... We have significant evidence to suggest. I'm going to stop there, okay? Because I don't have the problem in context. That's what you would say at the 5% level, okay? So write that down. At the 1% level, I would say fail to reject, okay? because 0.0143 is bigger than 1%. We have insufficient evidence to suggest ... because I don't have context. Okay, makes sense. So there's that at the 1% level. Okay, this is cool. We're kind of breaking it down for you here, just step by step. All right, now part B says if the alternative hypothesis was P is not 0.5, and I'll write that out how you would probably see it. It would be equals not 0.5. What conclusion would you draw at the 5% level? All right, pretty cool. So let's bring back in the calculation we just got done doing, okay? Let's bring that back in. There's that calculation, 0.0143, okay? Now, remember, we did a one-sided test, and let me draw this out for you. Make sure you got this correct. A one-sided test is greater than or less than, okay? And this is a one-sided test because I was testing the z-score 2.19, which is down in the right-hand tail, up to infinity on the right-hand side. All of a sudden, they ask you, HA is now pi or P is not 0.5. That is a two-sided test. In a two-sided test, what you do is you take your test statistic, 2.19, and calculate it, and we got 0.0143. Then you have to double it to take it from one side to two side. So it's pretty obvious what to do. I'm going to multiply this times 2. Well, that's going to make that p-value much, much bigger. Okay. So now what do you do with the test statistic is doubled? Now we have 0.0285. Okay, now the test statistic is 0.0285. So let me go back to this. Okay. So the p-value, shouldn't say test, the p-value is now, p-value is 0.0285. Well, interestingly enough, this doesn't change a thing because doubling it, it's still below 5% and still above 1%. So I'm going to write it out again. At the 5% level, our conclusion would be reject HO. We have sufficient evidence to suggest, and we don't have any context. I'm just going to put ... Okay, we have sufficient evidence to suggest ... Clear that. And again, 0.0285 is the number. At the 1% level, it's bigger, so it's failed to reject HO. We have insufficient evidence to suggest ... Okay. So sometimes when you double a p-value, it goes over the alpha level. It changes the result. In this case, it didn't. Okay. All right. Now, all of that is kind of a warm-up for this last question. So really, this is kind of a one-question question. These are the kind of things you're going to see on the AP test. When you get a free response question, boom, here it is. Okay, so this is page 571, number 41. I think this is another assignment in the homework. Okay, so this is much more likely to happen on your test. So we have a question. We hear that newborn babies are more likely to be boys than girls. Is this true? A random sample, this is a huge sample, 25,468 firstborn children included 13,173 boys. Do these data, by the way, this is considered plural, datum is singular, data is plural, give convincing evidence that firstborn children are more likely to be boys than girls? Just out of curiosity, I'm going to go ahead and pump in these numbers. I'm curious as to what percentage this is. So 13,173 divided by 25,468. It's about 52% boys. That doesn't sound like it's a lot more than 50%, but with that big of a sample, I think it's probably pretty significant. I mean, in terms of evidence, I mean, that's, you know, the larger the sample, the less the discrepancy can be. That's okay. So there's kind of a sense of it. Okay. So we seem to have more boys than girls in firstborn. All right. So they asked, do this data give you evidence? This is a 4-part response. This is, you have to do a 4-part response. So let's walk through it step by step. So you need lots of paper on this. So first thing, HO. Let's do a good job on this. HO. I'm going to put, I'm going to use pi. You could use P is equal to 50%. Because we're thinking it's supposed to be 50-50. Okay, so I'm just going to put boys and girls born same rate. All right, HA. Pi is greater than 0.5. Boys born more often than girls. Okay, so there's your HOHE. That's step 1 of the 4-part response. So get that written down. I'm going to clear this. Okay, so there's the first step. And again, you can use the symbol P here instead of pi. I just like to use the Greek symbols for HO and HA, and the kind of the Arabic symbols are lettering system for the statistic. Okay, all right, let me clear that. Okay, now the next step is the assumptions. So we're going to assume the following. Assume ... Okay. We have a representative sample. Representative sample. Okay, it's a large sample. Okay. There are greater than, I'll put a 0 on this, 250,000. We'll do it 254, comma 680 people born. For sure, there's millions upon millions. Okay, and that's the 10% rule. I'm going to just write that in. I like writing that because I think it shows the reader that, hey, this guy knows what he's talking about. Okay, all births are independent. What is that in practical purposes? I'm not really sure. I mean, even if it's twins firstborn and somebody's born first, so all births independent. Then the N in normal, well, we're going to have way more than 10 on this, so I'll just write it out real quick. So I think the percentage was 52%. So I'm just going to write this. So 25,468 times 0.52, which was the percentage, is greater than 10 for sure. And then 25,468 times 0.48 is bigger than 10. So we're going to have a normal curve. I'm just going to write normal curve. Okay, so there you go. There's your assumptions. 4 of them. Notice I bullet pointed them. I don't put the acronym SPIN. I don't want that showing up anywhere, but it looks good. I know my handwriting is sloppy, but you get the idea. Now, let's run the test. Now, the test is probably going to be run with software, but you need to draw the normal curve properly, okay? So let's check this out. All right, so let me bring the calculator in. Remember those numbers here. All right, so I'm going to go stat and then arrow over to tests. And I'm going to go one prop Z, okay? One prop Z test, number 5. Now, I'm going to try the HOHA is 0.5. Now, this is where you put X and N. So it's 13,173. And then N is 25,468. Okay. And we're wondering if boys are born slightly higher, so it's greater than. I'm going to click the draw button. It's going to do it all for me. This is probably going to be how you do it. Let me slide this up here. So there you go. So remember how to set this up, because we want raw score, z-score, percentile, like I've coached you to do. So I'll use this right here. So 0.5 goes here. Okay. 0.52 goes out here. That was the percentage of boys being born first. Then the z-score was 5.50. And then the p-value is approximately 0. Remember, that's how I want you to do it, all right? And then put the standard deviation here, okay? The standard deviation will be p 1 minus p over n, and n was that massive number. What was it? 25,000. We look again. 25,468. Okay. So that's going to be 25,468. Okay, that's here. So that's how I want you to dress that up. Okay, remember, I'm going to change colors here. Remember, what goes here is HOHA. What goes here is the fraction, that's the statistic that you got. What goes here is the z-score. And what goes here is the p-value. If it's 0, put approximately, and make sure you put the standard deviation here. That's how you get credit. If you don't do it that way, you may get marked down for calculator dumping. Even though you are dumping the stuff on the calculator, you want to organize it in a way that shows that you know what you're talking about. So that's step 3. There's a lot of room on your notes there. Probably got a lot going on there. Now, the last part is the conclusion. The conclusion, the p-value was 0. And there's a lot of ways to write the conclusion, but let me go ahead and just write it kind of formally. I'll make it a little longer. You've seen different ways of doing this, and you should know how to do it, but I'm going to write the word conclusion. Okay. Now, this question does not have an alpha level, 0.01 or 0.05. It doesn't have one. If it doesn't have one, just pick one. And in this case, it doesn't matter because it's below both of 0.1 and 0.05. So I'm going to put reject HO at alpha 0.01. Okay. Sometimes I write that, sometimes I don't. Let me sometimes I write that, sometimes I don't. It's kind of cool to write that. Okay. We have sufficient or significant, either way, sufficient evidence to suggest. Now, to suggest, earlier on, I put ... I had no context, but now I have context. Suggest that this is about firstborn kids, that firstborn children are male more than 50% of the time. Now, not much more, but it is a little bit more of the time. Okay? So that's your conclusion. So there's your 4-part response. So when they ask you a simple question on the AP test like this. This is actually required you to do all 4 parts. HOHA, requirements, test, conclusion. A lot of times, inexperienced kids will just do the 3rd part where they run the test if they're evidence, but they want you to do all 4 parts, okay, to kind of prove something. Considered a proof. We don't call it that. It's test of significance, okay? So that's pretty cool. Hopefully that helps. Now, the last part, little question was, to what population can the results of this study be generalized? All children or firstborn children? I think the study was just firstborn children. It wasn't all children, so it could only apply to that. So this is a really easy answer, but I will write it out. So I'll put because, I guess you shouldn't start a sentence with because, but I am. Because this study was only about firstborn children, then the conclusion only applies to them. How's that? Okay, there's some homework. Good luck, Stat Nation. Talk to you soon.